It's my pleasure to welcome you here for this session of ICCD 2020 conference in very specific conditions, but we still managed to have a very interesting program, and we will have 6 papers in this session about hardware accelerators for neural networks. And during the presentation, I invite you to send your questions to the speakers using the chat. And at the end of the presentation on the video, when I stop the video, I will ask your question to the speakers. So I will invite the speakers to turn on their camera and their microphone in order to answer the questions. So let's start with the first presentation right now. I need to share my here my screen and here. And so the first presentation will be made by Xiaowei Wang. Sorry if I miss the pronunciation, which is a fourth-year student, PhD student in computer science at the University of Michigan. So his research interests, of course, include in memory computing, machine learning, acceleration, and hardware and software co-design.
Hello, everyone. I'm Xiaowei. Today, I'm presenting our work, High-Throughput CNN Inference and Training with In-Cache Computation. A recent work called NeuroCache repurposes the last-level cache of CPU as bit serial computation units. The last-level cache is made up of multiple slices, and each slice is organized in 20 ways. Each way has 16 SRAM arrays. NeuroCache modifies the array peripherals to turn each bit line as an independent bit serial ALU. The NeuroCache work uses CNN inference as the workload. The convolution is done for all layers sequentially. At each layer, first, the filter weights of the CNN model is loaded from DRAM to cache. Then, the input activation data stored on cache are loaded to the correct arrays to perform in-array computation. Then, after the MAC and reduction computation, the results are transferred to the allocated space on cache, which are then used as the inputs of the next layer. Note that on each cache slice, out of the 20 ways, 18 ways are used for doing computation in parallel. 1 is used for buffering the activation data, and the final one is reserved for other CPU processes. The CNN inference in the baseline work focuses on the scenario where there is only one input image. In this work, we consider the inference with a batch of images as the inputs. A naive solution would be to repeat the entire inference process sequentially on each image. This would maintain the single image latency, but the data reuse of batching is not leveraged. An improvement is to reuse the weights across multiple input images. To do so, the computation is done layer by layer. At the beginning of each layer, the weight for that particular layer is loaded, and then the convolutions are done sequentially for all images in that batch, saving the weight loading time, leading to a higher throughput. However, as there are multiple input images in a batch, the storage space needed for the input activations increase, and they may not be able to fit in the on-chip space anymore and need to be offloaded to the main memory. This extra overhead of reading from and writing to memory degrades the throughput. To reduce the time to transfer activations between this cache and memory, the cache allocation policy can be changed. We can allocate more cache arrays as usual storage, but less as bitline computing units. Then more activations can be buffered on the cache, reducing the data movement time. On the other hand, the time for computation increases, but overall this can still lead to a performance improvement, as we will show shortly in the results. We also consider CNN training as a workload to accelerate in cache. The training procedure is more complicated and involves more intermediate data. This diagram shows a simple example of training with 2 images in a batch and 3 layers. We further apply the selective buffering strategy to optimize the performance of training. We choose the data to be buffered depending on the distance of the next usage in the procedure. Please refer to the paper for the details of this optimization. We use the 14-core Xeon processor with 35 megabytes of cache as the platform for in-cache computation, and we evaluate on the ResNet 50 CNN model. We use an in-house simulator for evaluating the in-cache computation performance. This figure shows the throughput results for the batched inference with varying cache partition strategy and different batch sizes. With the large partition strategy design space, the optimal result we achieve is 1.2x better than the original fixed partition strategy. Overall, we can see that for the larger batch sizes, the optimal partition is a relatively balanced point between computation and buffer, instead of devoting all cache resources for computation. Here is the training performance with our optimization. We vary the portion of cache used as buffer to demonstrate the effect of cache partition. Similar as batched inference, we see a better throughput achieved from a more balanced partition. The best training throughput achieved is 65.4 images per second. To conclude, in this work, we examine in-cache acceleration architecture and find out that memory traffic is time-consuming for batched inference and training. We propose new cache array partition strategies to enable trade-off between computation and data storage. Finally, we also propose selective data buffering to improve training performance. That's all for my presentation today. Thank you for your attention, and I'm happy to take questions.
Okay, so I see Xiaowei has already turned off his video. So I have a question regarding the implementation you did, and my question is, does the training require higher numerical precision than the inference? And if so, how do you handle that?
Okay, so yes, actually, we used the bfloat16 as the data format for training, where the inference uses 8-bit integer. So a high precision for training is needed for the fast convergence. And the implementation is that to compute with floating point numbers, the bit zero algorithm will be changed, where multiplication is done by multiplying the mantissa bits and adding the exponent bit. And then the addition or subtraction is done by first shifting the mantissa bits and then do the integer addition or subtraction.
Okay. Okay. So thank you very much for this answer. I can see that there is no other questions on the chat. I would like to thank you for the presentation and preparing the video and for answering my questions. And I propose to switch to the second paper of the session. Thank you again. So the second paper, so I need to share again and here. So the second paper of the session will be presented by Hongxiang Fan, who is currently pursuing a PhD degree in custom computing group in Imperial College in London, under the supervision of Professor Wayne Luke. He is interested in FPGA-based architectural and compression techniques for deep learning algorithms.
Hello everyone, my name is Hongxiang. I'm a third-year PhD student at Imperial College London. Today I'm going to present my paper, Optimizing FPGA-based CNN accelerator using differentiable neural architecture search. Our contribution includes, firstly, we propose an FPGA-based CNN accelerator with high resource efficiency. Secondly, we propose an accurate hardware performance model to speed up the performance estimation. Thirdly, we apply the hardware-aware differentiable neural architecture search to achieve high hardware performance as well as accuracy on the proposed FPGA-based CNN accelerator. Now, let's start from our hardware design. The system overview is presented in the slide. The host processor is used to set some hyperparameters of the whole system, including the number of channels and the number of filters. The intermediate results and the weights are stored in the off-chip memory. The FPGA system is used to perform the main computation of CNNs. To save resources, we run multiple convolutional layers on one processing engine. So the core module in our hardware design is function unit, which is used to perform the convolution, batch normalization, pooling, and shortcuts. Based on the hardware design, now we introduce our performance model, which includes loading time, storing time, and the computation time. The loading time means the time spent on loading inputs and weights from off-chip memory to on-chip memory, divided by the efficient I/O bandwidth. The similar formulation can be applied on storing time, which divides the amount of output data by the efficient I/O bandwidth. The last term is computation time, which is dominated by the amount of computation. Based on the proposed hardware design and the hardware performance model, now we introduce the neural architecture search for FPGA. An overview is illustrated in the slides. The search and the training are performed on GPU platform. The performance model is used for the fast performance estimation. The found neural network will be deployed on the proposed DNN Accelerator at the end of the whole process. The microarchitecture of the search space is presented in slides. The AnyNet block is a basic block in RegNet, which is a searchable cell in our paper. It's composed of a standard convolution followed by a group convolution with shortcut enabled. The domain for the kernel size and the group convolution is also presented in the table on slides. Now we introduce our experimental part. The hardware design is implemented on Intel Arena 10SX660 platform using Verilog. The quarters is used for synthesis and the clock frequency is 220 MHz. CIVA10 is used as our dataset with 10 classes for classification. Firstly, we test the accuracy of the performance model on VGG16, ResNet50, and Inception. The result is illustrated on the table. The prediction error is less than 5% on these three models, so it's accurate enough for estimating the hardware performance. Next, we compare our method with the existing work based on the reinforcement learning-based neural architecture search. We can improve the accuracy by nearly 10% while reducing the searching time from 108,000 to 25 GPU hours. So our future work includes validating our proposed method on the larger dataset such as ImageNet, integrating quantization and its effect into our neural architecture search framework, and improving the search strategies to reduce the search costs. So this is my presentation. If you have any question, please ask the question during the Q&A slide session or just email me. Thank you.
So thank you for this presentation.
I'm here. Can you hear me? Yeah. Hi.
Hi. I'm sorry.
Sorry.
We are sorry.
The video is playing in the background.
Yeah,
I think.
sorry. This
No
is
problem.
just. I don't know why I didn't stop the video on my. Sorry for that. Okay.
Yeah.
Excuse me. Not usual to manage a session by Zoom like this.
Yeah.
So you present some model to estimate the performance of implementing some neural networks on top of an FPGA. My main question is the fact that FPGA can be used by using reconfiguration. So you can have some, let's say, some reconfigurable parameters in your architecture, and can they be optimized all together with the neural architecture during your space exploration and performance evaluation?
Thanks for. Can anyone hear me?
Yes.
Yeah. Thanks for the question. So, Actually, this is exactly one of our future work. So we are planning to extend the search space of our framework to include some reconfigurable parameters and perform the hardware and algorithm co-design to achieve higher accuracy and hardware performance. So this is our one future work. Yeah.
Okay, and how your approach can be scalable in terms of size of the FPGA, but also in size of, because maybe I missed the information, and what was the complexity of the neural network you implemented, and is the framework can support some kind of scalability in the size of the neural networks, but also in the size of the FPGA and FPGA boards?
Yeah, so this is exactly what I'm planning to do. So in next step, I'm planning to build another resource model and include the resource constraint into our neural architecture search framework to consider the scalability of of the design on different hardware platforms, on different FPGA boards.
Okay. Okay.
Yeah.
So thank you for this answer. I don't have any other questions. And so thank you again for preparing the video and being here to answer the questions. Thank you. And so we will switch to the next presentation. And the next presentation will be done by, oh, I have some trouble here once again. Okay, this one. Not that one, here. So next presentation will be provided by Qinyi Sang. He's a PhD student at the University of Pittsburgh. And I guess that he introduces himself in this presentation, and which is quite a little bit longer than the previous one. So.
Hi, everyone. I am Xinyi. I will present my paper, Achieving Full Parallelism in LSTM via a unified accelerator design. This design targets on LSTM accelerator on FPGA device. Here are a few things about myself. I'm a PhD student at the University of Pittsburgh. My advisor is Professor Jintong Hu. My research interests include machine learning algorithm and resource-constrained device, machine learning algorithm auto-deployment on FPGA, neural architecture search, and resource-constrained device. My present will be in 3 sections: the background of LSTM, the unified accelerator design and its analytical model, the experiment result. I will introduce the LSTM background first. The full name of LSTM is long short-term memory, which is good at processing sequential data. It recurrently uses a single LSTM cell to process data at different timestamps. The input data at each timestamp is a vector, which will be extracted by the cell. The extracted data will be kept and applied on the next input. For more complicated applications, we can stack LSTM cell to form stacked layer LSTM or even bidirectional LSTM. These stacked cells share the same architecture, but not sharing the weight. Inside a LSTM cell, it uses gate to extract input data. The input gate, the forget gate, the output gate, and the cell state gate. The 4 gate results will be further processed to infer the cell output. We can see that the 4 gates have the same kind of computations. And in a cell, we can summarize 5 computing patterns. They are: the first one, multiply accumulate for input vector in length d, which is the data embedding size. Pattern 2, multiply accumulate for prior output in length h, which is the cell size. And both pattern 1 and 2 share the same number of matrix rows. And pattern 3, element-wise vector addition in length h. Pattern 4, element-wise vector multiplication in length h. And pattern 5, activations such as sigmoid and 10. Among the 5 computing patterns, pattern 1 and 2 are mostly computing intensive. Activation in pattern 5 are usually approximately computed. Here, the computing patterns are further labeled in the LSTM data flow. In each gate, the result of computing pattern 1 and 2 will be further computed in pattern 3. After activation, gate results will be further processed in pattern 3 and 4 to get the cell output. We can see that computing burden at each stage is different. The majority of the computing burden is in pattern 1 and 2. The existing accelerators on FPGA design a unique computing kernel for each computing pattern. For example, the 2 dedicated multiply accumulate kernel for pattern 1 and 2, we call it MAC. Dedicated element-wise operation kernel for pattern 3 and 4. Such design suffers from several problems. 1. The kernel synchronization, for example, synchronizing the MAC kernels. 2. Unbalanced kernel pipeline, such as the pipeline between MAC kernels and the element-wise kernel. 3. Low working frequency due to multiple dedicated kernels. 4. Low device resource utilization due to the unbalanced kernel size. Next, I will introduce my design, the unified LSTM accelerator and its analytical model. If we dig into a gate, we can find that the 2 MACs can be converted to element-wise operation like pattern 3 and 4. The original pattern 1 needs D multipliers with an adder tree, and pattern 2 needs H multipliers with an adder tree. Each row of the weight is multiplied with the vector and get accumulated. However, the weight matrix which are represented by the 2 blue blocks have the same number of rows, H. Here, let's keep in mind that computing patterns 3 and 4, they are in element-wise operation of size H as well. We can do the original MAC in the same element-wise fashion. First, each element of the vector multiplies its corresponding weight column. Second, we iterate all the vector elements and its corresponding weight columns. Third, we accumulate the products of vector element and weight element in the same row. Therefore, the 2 MACs can be processed via pattern 3 and 4 as well. And pattern 1 and 2 have the same matrix rows, so the conversion for pattern 1 and 2 are in the same computing size, but in different iterations. Now we can use only in pattern 3 and 4 a pair of element-wise vector multiplication and addition to process the entire LSTM gate. During computing, pattern 3 and 4 can be processed in 2-stage pipeline. For example, the weight column 1 element-wise product can be accumulated while computing column 2's element-wise product. With such a conversion, all computations in a gate can be processed via unified patterns. In this way, we can eliminate computing pattern 1 and 2, achieving the parallelism in each LSTM gate. The computing patterns are unified in pattern 3 and 4 of the same size. This brings chances in building unified computing kernel. Then we can recursively call the same kernel to process the entire LSTM. In this way, we can get rid of kernel synchronization and the unbalanced pipeline between computing kernels. With the unified computing patterns in one gate, the cross-gate parallelism can also be achieved by stacking the weight matrix of the 4 gates, which can increase the parallelism by a factor of 4. This is because the input vector is shared by the 4 gates, and the gate weight matrix are independent of each other. Such flexible parallelism can be taken advantage by devices such as FPGAs. A highly parallel computing core can easily fully utilize the device resource, and it is also friendly for on-chip data flow arrangement. Considering the device resources, the maximum size of the proposed computing kernel is 4 times of edge, and the device can have multiple such computing kernel if the buffer is supported. We also built an analytical model to mitigate the gap between the accelerator design and the hardware features, such as DSPs, the block RAMs on FPGA. With the given FPGA and LSTM, the analytical model can determine, first, the computing kernel key parameters such as kernel size, the number of kernels, and the portion of weight that can be buffered on the chip. Number 2, device buffer management, such as the unit buffer size, the FPGA physical buffer size, and LSTM weight footprint size. Number 3, the running schedule of the accelerator. In section 3, I will introduce my experiment result. The experiment is performed on 2 FPGAs, a small LSTM on PINC-Z1 and a big LSTM on VC707. We got the runtime data on PINC-Z1 and applied analytical model on VC707. On PINC-Z1, we outperformed the reference design with 10 times less inference time in int16 data type, while the reference design does not support floating point data type. Our design can also fully utilize the PINC-Z1's DSP and block RAM resource to buffer all the weights on the chip. For VC707, our inference time is 40% less than the reference designs, and we can also fully utilize the device resource to buffer all the weights on the chip. And this is all for my today's presentation. Thanks for watching.
Okay, thank you very much for this presentation. So, Sini, are you here?
Yes. Hi there.
Okay. I don't see you on the. Okay. I have a question on the computing pattern. How the computing pattern conversion bring extra computation? How this computing brings extra computation in your flow and things like this?
Yeah. So first, I want to clarify the question is, you mean will the conversion bring extra computation?
Exactly. Yes.
The answer is no. The conversion will not bring extra computation, but it actually changed the way, the order to compute. So for a basic matrix column, matrix vector computation, we will do row by row, but we change the way to accumulate all the vector. So we changed the way to compute it, but we don't bring extra computations. The number of computations are the same, but we accumulate each element.
Oh, okay. So, okay. So thank you. And I see that the time is running out. So let's switch, as there is no other questions in the chat. Let's switch to the next presentation, which will be done by Sheng Chu. So I have to here. Here. Okay, so the next presentation will be done by Cheng Chu, which is a master student from Hefei University of Technology, and his research field is on deep learning accelerator.
Hello everyone, I'm Cheng Chu from Hefei University of Technology. I will give a presentation of our recent work named a hybrid computing architecture for fault tolerance deep learning accelerators. This slide gives an outline about what I will present next. First is the background. The great success of deep learning motivates the development of deep learning in numerous domains of applications. Many of the applications, such as autonomous driving and agile and intelligent medical monitoring and treatment, are closely related to the safety of human beings and are mission critical. When deep learning models are applied in these mission-critical applications, the reliability of the execution is of vital importance and must be considered comprehensively. Deep learning accelerators typically consist of a large regular computing array and a set of on-chip buffers. The on-chip buffers usually implemented with SRAMs can be protected effectively with ECC. For faults in PE, the exciting work mainly includes two types. The first is to seek to use the inherent fault tolerance of the neural network model by retraining the model specific for the faulty computing array, but the cost of retraining is very high. The second category of approaches aims to recover the faulty PE computing array with redundant PEs. It uses redundant PE to recover any faulty PE in the same row or clone. The next is our motivation. To analyze the influence of faulty computing array, we inject random bit flip errors to register of the PEs in a 32x8 computing array. The dataset we used is MINIST and the model we used is LENet. LENet is simple and thus relatively resilient to faults. The situation can be worse given larger dataset and more complex models. For each bit error injection rate, we generate 50 fault configurations with different random seeds and evaluate the prediction accuracy. The results show that the prediction accuracy varies dramatically across the different fault configurations. The prediction accuracy may drop considerably even on the very low error injection rate, thereby protecting the computing array is necessary for mission-critical applications. We also evaluate the classical hardware redundancy strategies, row, clone, diagonal redundancy method for the regular 2D computing array and measure the fully functional probability of the computing array on the different P error rate. The results show that these classical redundancy design approaches can hardly mitigate all the faulty PEs even when the P error rate is 1%, and as the fault injection rate increases, the situation gets worse. Here comes our hybrid computing architecture. In order to tolerate various fault configurations, we proposed a hybrid computing architecture HCA which has a dot production processing unit seated along with the 2D computing array to recompute all the operations mapped on the faulty PEs. It selects both input features and waits to conduct the dot production on DPPU concurrently with the original 2D computing array in the DRA. However, the data flows in the 2D computing array and the DPPU are different. As a result, data read from the input buffer and wait buffer for the 2D computing array cannot be reused directly by the DPPU. So we introduce a wait register file to back up the latest waits consumed by the 2D array. The addresses used to select the wait and input feature are generated by an address generation unit AGU based on the faulty PE table, which records the location of the fault PEs. The result of DPPU are stored in a registers and then written back to the output buffer sequentially when the output buffer port is available. To further illustrate the data flow in both the 2D computer array and the DPPU, we present an example in figure. At cycle k times k times c, the first clones of PE writes the calculated output feature to the output buffer and starts the calculation of new output features. Since PE10 is faulty, the result written to the output buffer from this PE was wrong, while the input feature and weights that are used to calculate the result remain in the input buffer and pin weight register file. They can be read and used to recompute the output feature on DPPU. At cycle k times c plus 15, the pin weight register file are filled with weights and they will be kept for 16 cycles, with coming in next cycle will overwrite data in pin weight register file. Afterwards, the processing iterates like the first processing step until the end of the calculation. At cycle k times plus 16, when all the clones of PEs write output feature data to output buffer, each PE may only conduct local accumulation because input channel is usually much larger than 16, and it takes more cycle to obtain new output features. So the recomputed output feature can be updated to the output buffer without conflict. At cycle k times c plus 18, all the computing on 40 PEs are updated in the output buffer. Both the 2D computing array and the TPPU conduct the partial convolution locally, so the output port is idle before the first clone of PE completes a new output future calculation. When the number of fault PE in the 2D array is smaller than the TPPU size, the fault can be fully repaired with recomputing on TPPU. When the number of the fault PE further increases, the repair time of TPPU will degrade the performance of the entire system. To avoid the performance degradation caused by the store of 2D computing array, we discard the sum of fault PEs such that TPPU can mitigate the risk of the fault PEs. In order to improve the flexibility of TPPU, we have added redundant operators to TPPU. Basically, the multipliers used in TPPU are divided into multiply groups, and each group is equipped with a redundant multiplier. When any multiplier fails, you can immediately replace it with its upstream multiplier. Similarly, we also use redundant design to protect the adders in the adder tree. Next is the evaluation. The specific parameters of the accelerator are shown in the table. In order to evaluate the reliability of redundancy design, we have two different failure distribution models, namely random distribution model and cluster distribution model. And we use a set of representative neural network models including AlexNet, VGG, ResNet, and EULO as benchmark. We compared the chip area of DLA with different redundant computing architectures. Since the 2D computing array is 32 by 16, the clone and diagonal redundancy strategy consist of more PEs that occupy more chip area. At the same time, the diagonal redundancy consists of more muxes that's consuming more chip area. HCA requires 16 multipliers and adders which only occupy a fractional or chip area. However, HCA needs to add a read port to the input buffer. As a result, the total chip area of HCA is larger than RR and CR, but still smaller than DR. We evaluate the fully functional probability of the accelerators. Since the TPPU size is 16, the probability drops to 0 when the number of the fault PEs exceeds 16 and 3% PE error rate. Nevertheless, the probability drops slightly when the PE error rate is less than 3%. The drop is mainly caused by the degradation of the array size. The advantage of HCA are more significantly on the cluster fault distribution model because HCA is not affected by the uneven fault distribution. When the applications do not require fully functional accelerators, we may have more design options to maintain the functional with performance degradations. In this case, the remain computing power becomes critical. Figure shows the remain computer power normalized to that of the DRAs without hard faults. It can be observed that the HCA shows much higher computing power under all the different PE error rate, and the performance gap enlarges with the increase of the PE error rate. This is mainly caused by the flexibility of HCA that allows the TPPU to select the most critical 40 PEs to repair, such that the remain computing array can be larger. To gain insight of TPPU, we investigate the scalability of the fault tolerance design approaches by evaluating 3 DLA with different computing array size. We compare RR and HCA, which includes the same number of redundant PEs under the 3 array configurations. The result shows that HCA keeps similar fully functional probability when the computing array size scaled. In contrast, the fully functional probability deteriorates with the increase of the array size. We also compared the repair capability of TPPU of different size under a fixed array scale. Given a fixed computing array size 32 by 16, we scale the TPPU size from 8 to 32 and mirror the fully functional probability. The result is shown in the figure, and it shows that the fully functional probability improves proportional to the TPPU size, which also demonstrates the high scalability of the proposed HCA. Finally, there are our conclusions. We proposed an HCA and have a TPPU to recompute all the operations mapped on the 40 PEs in the 2D computer array. When the number of 40 PEs in the 2D computer array is less than the TPPU size, HCA can fully repair the 2D computer array despite the fault configuration. Even when the 40 error rate further increased, TPPU can be used to repair the most critical PEs first to ensure a large continuous computing array. That's all. Thank you.
Okay, thank you for this nice presentation. Finally, did you see the presentation? I hope that, because I missed some. Okay. I have a question, because maybe I missed the things in your presentation. I suppose that the fault model that you consider in your work is a permanent fault model, right? So it means that you consider that the processing element has an error, and but what is the fault model you consider?
Hello, Professor. Can you hear me?
Yes, I can.
For our design, for the deletion problem, you mean the problem is the deletion problem? Yeah.
I mean that you propose some fault mitigation techniques in the array, and but I would like to be sure that you consider what kind of fault did you consider? What is the fault model? Do you consider, for example, some transient fault or permanent fault in the processing elements?
The fault model, in the PPT, I say the fault model is we have two fault distribution model, the random distribution model and the cluster distribution model.
Oh, yes, okay, I saw that in your results. My main concern is the fact that, do you consider that you have a permanent fault in the processing element that trigger a mitigation using the DPPA to recompute the things, or can you consider, in fact, the main question under this is, can you consider some transient fault in your work, or it is too costly to recompute all the things depending on the So I guess that you consider some permanent fault. So it means that a processing element becomes faulty. And how do you detect the fault? Because you propose some different strategies to mitigate. And how do you control the mitigation strategy? Because as you can remove some rows of faulty PE, and but how do you decide this? Do you have a kind of level, and how do you control things, and how do you detect the faulty PE?
First, we detect the faulty PE. We use the instruction to control the data flow to achieve the effect of the deletion. In many accelerators, the accelerator is controlled by instructions. So when we need to delete the clone, we copy the input date of the deleted clones to the nearby clone through the instructions, and and this is the case for every subsequent clone. In this way, the deleted clone is equivalent to just a clone of registers. When the accelerators is started, it will affect the cycle, but when each clone of accelerators is being calculated, it will no longer affect the overall performance. Yeah.
Oh, okay. Okay. So thank you for preparing the video and to answer my questions. Let's go ahead on the next presentation. Okay. Okay. So next presentation will be provided by, has been prepared by Jianhao Chen, which completed his master's degree in computer engineering at the Texas University, and he's worked on the research of the optimization of on-chip power delivery networks.
I'm happy to present our work on dynamic heterogeneous voltage regulation for systolic array-based DNN accelerators. With the development of machine learning algorithms, there have been enormous research works on deep neural network accelerators in order to accelerate computation and reduce energy consumption. They have been applied on mobile devices and data centers.
The increasing power and a non-uniform workload distribution have made power delivery network design for DNN accelerators much more challenging. A power delivery network converts down the PCB supply voltage with voltage regulators and uses power grids to deliver power to transistors of the hardware. For voltage regulators, they can be applied on-chip or off-chip. They can be switching voltage regulators or linear voltage regulators. As for the hardware, there have been many research works for CPUs and GPUs, but no research has been done on PDN designs for novel DNN accelerators. There have been many PDN designs optimized for CPUs to reduce energy loss and ensure power integrity. They use power models and architectural simulations to assess the performance of their novel PDN designs. The optimizations include using on-chip voltage regulators, optimizing PDN control policy and architecture, and using multiple types and layers of voltage regulators. On the other side, there are also many research works on energy analysis and optimization for DNN accelerators. One field is to prune the network to reduce energy consumption, and they developed power models for energy analysis. The other field is accelerator simulation, where RTL simulators and architectural simulators are developed. However, there are no research works concerning the PDN design for high power consuming DNN accelerators. Therefore, in this work, we try to combine the research on PDN designs for traditional computing hardware like CPUs and GPUs and the research on novel DNN accelerators. We designed and optimized the power delivery network for DNN accelerators with high power consumption. In this work, we built a power modeling framework by using existing simulators and our own simulators for architectural simulation and building power models based on published works. We designed heterogeneous voltage regulation PDN architecture and optimized the PDN based on characteristics of the hardware. We achieved significant energy saving without introducing large overhead. To start with, we modeled the Systolic array, which is a popular architecture adopted by many accelerators. It includes processing elements and on-chip memory. There have been intensive research on this type of DNN accelerators. Then we built a power modeling framework for Systolic array-based DNN accelerators. First, we generate utilization statistics using architectural simulators. Then we generate power traces using power models. For processing elements, we run the actual neural network to generate utilization statistics and calculate power consumption using unit computation energy. For memory, we used ScaleSim as the architectural simulator and Cacti as the power model. For the basic PDN architecture, we used HVR architecture, which was designed for multi-core CPUs. It has multi-layer voltage conversion and heterogeneous voltage regulators, including on-chip LDO, on-chip buck converters, and off-chip buck converters. It also has a control policy used to control the intermediate conversion voltage and the number of active voltage regulators based on the workload. Then we try to optimize the control policy of HVR architecture for Systolic array-based DNN accelerators. First, we modeled two types of data flow in Systolic array, output stationary and wait stationary. In both scenarios, the utilization of processing elements in the array depends on the characteristics of the convolution layers, and the operation of these processing elements doesn't start at the same time. First, using our power modeling method, We found that during operation or idle mode, the temporal variation of the hardware workload is small and is less likely to cause any voltage violations. While during the startup phase of the computation of a layer, large amount of processing elements start to operate, which creates a large current surge and can cause voltage violations. So the on-chip LDO input voltage is boosted based on a safe estimation of the amount of current surge. Besides, we use power gating to shut down the processing elements that are unused. In both output stationary and wait stationary, the number of active columns is determined by the number of kernels in a layer, which can have a big variation in a neural network. So we divide the power domains by columns. We utilize proposed power modeling framework to assess the performance of the proposed PDN architecture and control policy. We consider a 65 nanometer 100 MHz accelerator with an array size of 256 by 256. The chip area and power consumption data are from published researches. We assume leakage power to be 40% of the total chip power based on published papers. As for neural networks, we used models from MLPerf, which are selected to well represent both light and heavy CN workload conditions. Before energy evaluation, all PDN architectures and control policies are configured to have the same level of power integrity for fair comparison. We adopted two-stage and three-stage PDN architectures, where a two-stage PDN includes off-chip buck converters and on-chip buck converters, while a three-stage PDN includes on-chip LDO in addition. The control policies are set to be static or dynamic, where the control variables in the system remain static or dynamic. First, we compare the energy overhead for PDNs with single power domain. For each particular benchmark DNN, all evaluated schemes supply the same amount of energy to an accelerator, while they have the different energy overheads due to different PDN setups. The PDN energy overhead are broken down to those of LDO regulators, the on-chip buck converters, the package, and off-chip buck converters. All energy components are normalized with respect to the total energy consumed for running the corresponding benchmark in each case. Among all schemes, the three-stage PDN with dynamic control lead to the lowest energy overhead for all benchmarks and for both data flows. The energy overhead is reduced by up to 10.21% compared to those of the two-stage static PDN. Next, we evaluate the additional energy savings brought by power gating. The energy dissipations are normalized with respect to the maximum energy delivered to the accelerator among all PDN schemes for each benchmark. These maximum values correspond to the energy dissipated by the accelerator without power gating. The power gating reduces PDN energy overhead by up to 5.1 times and leakage energy by up to 5.3 times. The results suggest that fine-grained power gating with more than 4 power domains has less additional benefits for heavyweight models with a larger average number of filters per layer. And SSD applications benefit more since they have a higher percentage of layers with fewer filters. Here are the conclusions. Using HVR PDN architecture and the proposed dynamic control policy reduced energy overhead by up to 10.21% without large hardware overhead. Coarse-grained power gating with less than 8 power domains implemented saves significant amount of energy. The PDN energy overhead is reduced by up to 5.1 times and the leakage energy is reduced by up to 5.3 times. Thank you for listening.
Okay, thank you very much for this presentation. Okay, so Maybe I have I don't understand why finally energy savings is reduced when you increase the number of power domain. Can you maybe provide us some insight on that?
Yeah. So our power saving comes from the power gating is basically by shutting down the unused processing elements. However, there should be necessary amount of processing elements used to do the computation. However, increasing the number of power domains just may not increase the number of unused power processing elements, because there's still some require the necessary amount of them to do the computation. So yeah, so we have demonstrated that coerced division of power domain have already achieved a significant amount of power saving, but I think that's all we can do for now.
Okay. So thank you for preparing the video and for this answer. And we are running out of the session, and we still have one presentation to follow. Thank you again. So the last presentation for this session will be done by Ryuk Xu, which is a PhD student of the National University of Defense Technology, and is working on accelerating deep learning and providing some architecture for that.
Hello everyone, I'm Rishu. Today I will introduce our work, CMSA, Configurable Multidirectional Systolic Area for Convolutional Neural Networks. Many hardware accelerators for CNNs have been proposed, like TPU, 是电脑, Eros, Germany. And we find many hardware accelerators choose the systolic area architecture. The main reason is the simple design and high reuse state chance. These figures show the workflow of a systolic area. First, convolution is converted to general matrix multiplied by image-to-core algorithm. Then the data is divided into many tails and fed to the area. The dimension of tails is decided by the architecture of the systolic area. In general, these tails or matrices are suitable for the systolic area. The processing elements, or PEs, in systolic area can be fully activated. However, some special convolution bring the challenges for systolic area, like small-scale convolution. The dimension of input feature maps is small, so the input matrix cannot activate all the PEs. Another situation is depthwise convolution. These convolutions are widely used in complex CNNs. The weight data shrinking into the vector and cause lots of PE idle. The problem is the systolic area architecture is lack of flexibility. The design intention of systolic area is simple and efficient. So it means fixed data mapping or data flow. So we propose a configurable multidirectional systolic area, CMSA, to make systolic area more flexible. The main design objectives of CMSA include optimization for small-scale convolution and optimization for depthwise convolution. For small-scale convolution, we split the area into two parts. In this case, the input feature dimension suitable for the systolic area is halved. It can solve the problem of small-scale convolution. For depthwise convolution, we decide to change the data mapping strategy. Left figure shows the workflow of this strategy. It uses daily units, such as register seeds, to enroll the weight data to two dimensions. However, the scale of enrolling is often small, and the PE in the area cannot be effectively used. So we stretch it into one dimension which is more conducive to scale up. We can also afford it to take up more PEs. To support the above optimization, CMSA's architecture is also relatively special. First, the data transmission in the area is bidirectional. In addition, there is extra buffer to provide data for the area from the bottom. The structure of PE must also be adjusted. This is a regional PE structure composed of input, wait, output registers, and arithmetic units. This simple structure only supports a single data transmission direction. This is a CMSA PE structure. A new data path has been added, which is the new data transmission direction. The transmission model can also be changed. The Roman numeral 1 represents the broadcast model, and the Roman numeral 2 represents the systolic model. At the same time, the output data direction can also be changed. Depends on the location of the PE. The output register can be used as a DNN unit. This design greatly increases the flexibility of the area. In the experimental part, we evaluate the PE utilization rate of the areas at different scales. CMSA always be better than traditional systolic areas. The evaluation proves that for small-scale convolution, CMSA can increases PE utilization rate by up to 1.6 times. For Depthwise Convolution by up to 14.8 times. That's all. Thank you for your watching.
Okay, thank you very much for this presentation and this introduction. Did you make a comparison of the hardware overhead of your solution against the traditional approach? So you gain in resource usage, but did you evaluate the overhead and the cost of your solution?
Hello?
Hello?
Wait. Hello?
Yes.
Professor?
The sound is not that good, but hello?
Hello, Professor?
Yeah. Yes.
Can you hear
okay.
me?
Yes, I hear you.
Yeah. Can you repeat your question?
Yes, you did not present the hardware overhead of your solution against the traditional approach. So you gain in resource usage, but as you had some additional resources, what is the overhead of the solution proposed? In terms of hardware. Hello?
Sorry, I don't understand your what's your meaning. Can you
okay? So anyway, so my main question and my main concern is to evaluate the cost, the overhead cost in hardware of the solution of your solution against the traditional approach. Okay, so anyway, so that's not a big deal on the because we are out of time right now. We spent 6 additional minutes in this session. So I would like to thank you all the speakers for preparing the video and being here to answer the questions. I would like to thank you all to attend this session on the hardware accelerator for neural networks in this very specific context. And I wish you a good day if you are in the morning, and maybe a good end of the day if you are in the afternoon, depending on your place in the world. And stay safe, and thank you for attending. Thank you all.